Okay, this is an English presentation, so I'm going to start in English. Welcome everybody to this fourth PhD encounter, or encuentros doctorales. This is the fourth encuentro held by Intelligent System Lab. In this encounter, we're going to have three presentations from the three PhD students. That's for them is their second presentation. I think for Abdullah it's even the third presentation. So he's really developed in his PhD. So I'm not gonna say anything further because we are already too late. So I just wanted to thank you all for coming. I hope you're going to enjoy this presentation, this new presentation. Just go ahead.
Okay, thank you. Okay, good morning, and thank you for joining us our workshop. Today, as a continuum of my work, I will present the part of obstacle detection and avoidance. It's a part of the autonomous navigation systems. As the outline of the presentation, we will start with the introduction. In the introduction, we will define our problem and we will search about the solutions. Then we will talk about our objective. After that, we will see some related works of our vision-based obstacle navigation systems. Then we will talk about the proposed approaches. We will see the detection approach, and we will see the results. Then we will talk about the avoidance algorithm. And at the end, we will talk about conclude some conclusions, and we'll talk about the future work. Starting from our introduction, the problem is that the obstacle detection is considered as an important part of the autonomous navigation systems. And this part is very challenging, especially when we work with a small and micro aerial vehicles. That's because these vehicles cannot carry external loads like laser or radar. So we find that because of the advantages of the lightweight of the camera and the lower consuming of the power, it will be the suitable solution of our work is the obstacle detection. So we will work about vision-based obstacle detection. And here specifically we will detect the obstacle using just a single camera. Okay, so it's a monocular vision-based obstacle detection. The objective. Let's imagine that we have a start point and the end point. And we have a path, predefined path. This path is divided in several waypoints. We have the drone. This drone should follow the predefined path from start to end. While moving, suddenly we have this guy talking in WhatsApp in front of the drone. So we have two options. Or hit this guy and cut his fingers like Enrique Iglesias, or avoid him. So when we're getting more close to the person or to the obstacle, the drone senses that we have something in front of us and start to create a new waypoint, follow this new waypoint, and then recalculate its position to go back to the predefined path. So go to its path. Again, it's moving. We find this pretty girl. So detect this girl and create a new waypoint. Go to the new waypoint, recalculate the position, and go back to its path. So from the green one is the predefined path. We have a new path that created the drone because it found some obstacles in front. Okay, this is the objective. The related work. In the point of view of the vision, we have three main categories of obstacle detection, or let's say detecting the distance of the obstacles or objects. First one, we call it motion parallax. The motion parallax is the phenomena that, imagine we are in the car and looking outside, we see the moving objects. So the closer objects, the movement of the closer objects is faster than the farthest one. So the difference between these movements, we call it motion parallax. As we can see here, the buildings is so far, so it moves slowly, where we have this is moving fast. An example of this is optical flow or extraction from motion. The problems of, or the limitations of this, we have an expensive computation costs. Also, we cannot detect the frontal obstacles. We just detect our side obstacles. The second category is stereo vision. Stereo vision, as we know, using two cameras to estimate the 3D information about. The limitations here is we need a sufficient baseline between the camera. But imagine we have a small drone, so we cannot find a sufficient baseline between the two cameras to get accuracy 3D informations. Another limitation we have, it's also expensive incubation times, and one of the more important limitations, till now we don't have a stereo camera with a lightweight, relative lightweight. The smallest one, I think, is the ASOS, and it has the weight of 230 grams. And for the micro drones, it's very, very heavy. So we cannot use it. The third category is the monocular cues. In the monocular cues, we have the ability to estimate a relative distance or a relative depth using just one camera. An example, we have a linear perspective. Using the detection of parallel lines, we can know if the object is far or closer. Another example is the texture gradient. Here, we can know the distance or the depth using the texture, where the closest objects we have a clearly textures, and we go smoother to the first one. Interposition. The interposition is the overlapping between objects. So if we have an object overlapping the other, we can estimate that one is closer than the other. No? As here, the finger and the earth. The depth from focus. The depth from focus also have the idea that the closest objects look sharp than the first one. That is Broly. And another example is the relative size. This is where we work. The relative size, we can estimate the size. From the size, we can estimate if the obstacle is closer or far, when we estimate the expanding of the size. This is the three categories, and we will work with the relative size estimation. So, the detection. In the title, we have a bio-inspired vision detection. So, a bio-inspired, we take this word because we try to mimic the human behavior of detection the obstacles. Let's imagine we are moving and we found this wall. So when we getting move more and closer, what we have, that the size is expanding. And one more time, it's expanding. Till a certain point, we can decide, no, stop. This is an obstacle. So we try to avoid. From this idea, we have our algorithm. So from our algorithm, as an input of our algorithm, of the detection algorithm, we have the image frames, a sequence of image frames. As an output, we have a state, obstacle or not, and if we have an obstacle, we will get the 2D position of this obstacle. Starting getting a sequence of frames, then we will select a patch from this frame. We will not work with the whole image, and that's why, because any objects or obstacles outside this area will not cause a danger of our drone. And also, just working with this patch minimize our computation time. Okay, so we define our workspace, detecting the key points or the features between the two consecutive frames, and we will get only, the algorithm return only that the key points that is symmetrical in the two frames, and only if the key point in the second image is greater than the key point in the first image. So we can start estimate that we are closing to the obstacle. Then we'll just draw and convex an area around the key points in the 2 points, and we will compare our key points from the 2 images and our area estimated from 2 images. So we will select as an obstacle if the area, the ratio of area of the second image to the first image is more than 1.7, and if the key point ratio expanding is more than 1.2. So we have an obstacle. This is we can see here detecting the obstacle. So we will take the position and go to algorithm 2. Algorithm 2 is the avoidance algorithm. Let's see some results here. An example here where we can detect a pattern. Just when detect, we have an hover, detect and stop. So the drone, just when it detects an obstacle, will stop, not move. Here we have the same with the top maneuver. So when detect an obstacle, go up. Another example, detecting a person. So when it detects a person, go left. Here we have detecting a wall. So when detecting a wall, just stop, hover. The avoidance algorithm. First, to make the avoidance, to make the maneuver, it should be the scale area less than 2 and the key point size is less than 1.5. That's why we can detect if it's 1.7, 1.2, and if we are so close to the object, so we can, the ratio is greater than 2. So here we will not do any maneuver, just to stop. If not, we will divide our workspace as 4 areas. If the obstacle exists in zone A or B or AB, so go down. If it's in CD or CD, so go up. If it's AC or AC, so go right. BD or BD, so go left. If it exists in 3 areas, so do the diagonal maneuver. And if it exists in the 4th in the whole patch, if it exists in the whole patch, what we have here, the first thing, we will take our next waypoint. We have next waypoint, we have this obstacle, so this obstacle is in the whole patch. We have our safety boundary, which is the 26 centimeters in the both sides and 15 centimeters in, in both top and down. So comparing the YZ with the YZ of the drone, and we can select the shortest path, or we have a side maneuver, or we will make a top-down maneuver, or we can do a diagonal maneuver. The equation of the maneuvering, just we changing the velocity. We consider that the drone moving with the constant velocity in x, so for any maneuver we can just change the side or top down, or both, if we need to make a diagonal maneuver. As a conclusion, we present two algorithms to detect and avoid obstacles. Our detection algorithm mimics the human behavior of detecting the approaching frontal obstacles. The algorithm is able to detect the obstacles between 80 and 120 centimeters, depending to the velocity of the drone, and our computational time is between 30 and 60 milliseconds, depending on the number of features in the image. As a future work, actually we don't have a future work because we still need to test our avoidance algorithm, which is in progress. And as an idea, as a future work, we can mix between 2 or 3 algorithms, just with our algorithm detecting the frontal, with detecting some side objects. That's all. Just I show briefly the 2 algorithms with some results. I hope you enjoy the presentation, and if we have any questions or preguntas or ideas.
How do you find the key points?
Actually, we use the SIFT algorithm to find the key points. There is a standard algorithm of detecting key points. So it just detects the key points. It gives you the size and the position of the key points. And we then compare the size. But we're using SIFT.
You classify the obstacles between static and dynamic obstacles?
It will be yes, because if you are moving and the obstacle is moving toward you, so we can detect it. But if you are moving and the obstacle is moving around, no. It should be closing, it should be approaching.
How do you know the odometry of the movement of the parrot?
This is from another camera. We have a vision-based odometry. I explained it last presentation. Just so we have, or we can use the gyroscope, but it's good using the visual from our drone. I mean, low cost. So we have the position from another camera is vertical camera, and we have the frontal camera to detect the obstacles.
Thank you.
Thank you.
Any more questions? I have one myself. Do you try to, or maybe are you thinking about doing it in future, to combine this feature detection with texture detection, so you can more or less know the size of the obstacle somehow? You can combine them somehow.
Combining with
texture, yeah, identification of texture, so you can more or less use it to identify how wide is the obstacle.
Yeah, it may be like a future work. That's what I'm talking. Yeah, yeah, it will be a good idea. Actually, the base of this detection, we need the texture. So, yeah, maybe.
Okay, thank you very much, Abdullah, for your nice presentation.
Thank you.
An applause.